Good.
Say, what about we spice it up today and we play a little round of ping pong?
Okay.
Okay. Are you ready for this? I never give up. Go get the ball.
Oh no, it's crushed.
My force was too impeccable. What will we do?
Science.
To old Charles.
His law will show us how to restore the ping pong ball to its original state.
So we can play ping pong without the dents. For this, we are going to need
Water and a stove.
and a pan and our damaged ball. Follow us to the stove and we will begin. So we are just going to place the ball inside our, what is this called? A pan?
It's a pot.
A pot. And we're going to turn up the heat to get it sizzling. And the ball is almost to its perfect. Oh, it is there. When did this happen? As you see, it's perfect now. The dents and scratches in the wood are gone. It's a perfect sphere. In our experiment, we used Charles' law. What is Charles's equation?
V1 over T1 equals V2 over T2.
All right. And now that we have this equation, we can plug in our own numbers to see what we got. Have that. What is our V1?
It's an X because we don't know what it is.
We don't know what our V1 is because that was the misshapen ping pong ball. And our temperature starting out was
294 degrees Kelvin.
294 degrees Kelvin, which equals our V2, which would be the full volume of the ping pong ball, which would be
0.033511546 liters.
okay. Well, quite a long number. And our T2, which would be our boiling point. Temperature 2 is 373 degrees Kelvin. And now to get our answer, we cross multiply, which would be 373x equals 294 times 0.033511546, which would be
9.85.
Okay, and now we just divide both sides by 373, which would get x equals
0.0264.
64 liters because this is V1. And so this is the answer. I gotta say, Will, I was pretty hyped up on science after that last experiment.
Yes.
So why stop there? Let's keep it going. Keep the fire alive. Okay, so for this next experiment, we are going to try and smush or crush this unbreakable can. Now, if you can see, it's very sturdy. I can't. Can you? You try. Give it a try. It's unbreakable, as you can see, by the human force. So we are going to
use Gay Lussac's law to crush the can.
Precisely. For this experiment, we're going to need our trusty tongs, our unbreakable can, and inside is filled with water, and the water is just room temperature. and then our pan. And then we have a bowl full of chilly cold water that has some ice with it. If you can see that. Can you see it close up? Close up. Can you see? It's very, very chilled. Okay, so we are going to begin. What were we going to start with?
Put the pan on the stove.
Put the pan on the stove. Follow us.
It's not lighting.
There we go. Fire. Fire. You see the fire? Okay. Now we're going to bring our trusty can, lay it on here. And when are we going to know when to take it off, Will?
When steam comes out of the hole.
Perfect. Did you hear that, everybody? When steam comes out of the hole. Okay, should we have our bowl close by? Mm-hmm. We're going to put it just right here. It's for you. Foreman right here. So, what we got going? Are you ready for this? Are you ready, Will? Now, as you know, it's got to be speedy quick, so stay with me here. Ready?
Mm-hmm.
Formula for Gay Lussac Law. And what was our P1, William?
258 ATM.
258 ATM. Over our T1, which was?
378 Kelvin.
378 Kelvin. And that equals P2, which is?
X.
Over T2, which is?
273 Kelvin.
273 Kelvin. Now, originally we had Celsius, but we cannot work with Celsius. So we added 273 to our Celsius temperature to get our Kelvin, in case you were just wondering about that. Okay, so now to solve this, we're going to cross multiply it. So that gets us 378x equals, Will, let's do the math.
70,434.
70,434. And we're going to divide both sides by 378, which is, Will?
186.3.
X equals 186.3. And that is our answer in, what was it?
ATM.
Pressure, so it is ATM.